Okay, so today we are going to start by talking about a couple of things, the birthday paradox and the Monty Hall paradox. So remember last time we finished with the Monty Hall paradox, I'd outlined what the paradox was to you, and then we were going to think about how to solve it, what was the, what the question was. So, okay, so before that, let's start first with the birthday paradox. So what it has to do with is this question about, so you're given a class with n students, where n is smaller than 365. And sorry. Okay. Okay. N is smaller than 365, and these n students wish to compare whether any two of them have the same birthday. We want to know share birthday. And so the question is, how large should n be before you have roughly, say, a 50% chance of having the same birthday, of having any two having the same birthday? Okay, so you have 365 people, you have n people, you have 365 days in a year. You want to know how big should n be before you have two people having the same birthday? Now, one thing that you might imagine is that n equal to 365 over 2 would be the right answer. Okay, so what you want is probability, say, 1/2 of this event, that two of them share a birthday. You might imagine that the right answer is 365 over 2. It turns out to be the wrong answer. Okay? The right answer turns out to be something closer to 25. So actually, what is it? N approximately 25 gives you this answer. So at n equal to 25, the probability is about 0.57 already. So you might imagine that 25 is too small. How could it be that with 25 students, you already have over a 50% chance that at least two of them have the same birthday? So let's do this. Let's calculate this probability out. So let's let A be the event that at least 2 out of n students have same birthday. Okay, so what we want to figure out is what's the probability of A. Now, sometimes it turns out that some events are hard to figure out the probability of. So in this case, what we are going to do is we are going to look at an event B, which is the event that no two students have the same birthday. No two students share birthday. Turns out it's much easier to bound the probability of B. So how do you do that? Well, what you do is you count the cardinality of B divided by the cardinality of the sample space. Well, so, the question comes up, what's our sample space? So we have n students, and we want to know what's the birthday of each one, right? So what's our sample space consist of? Well, each point in the sample space consists of a birthday for each of the n students, right? So you have D1, D2 through D sub n, the n birthdays of the n students. And you have every possible way you can choose this, right? So D1 prime, D2 prime, Dn prime. So it's every possible way you can choose the n birthdays. So how many ways are there of choosing the n birthdays for these n students? Yeah, so the number of points in the sample space is 365 to the n. Okay. Now, of these 365 to the n, how many of these sample points actually sit inside B? So B is some subset of omega, right? It's only those points where D1 is not equal to D2, is not equal to D3, is not equal to Dn. So all these days are different from each other. So now we want to know how many such points are there where all these n days are different, distinct from each other, right? So how do we count the number of points in B? I'm sorry? It's 365 choose n. Well, except remember here, when we counted 365 to the n, we were saying the order matters of which order these people are in. So we want to still choose them in the same, where the order matters. So yeah, so what we want to do is we want to use the first rule of counting. Right? We say, well, the number of ways of choosing the birthday of the first student is 365. And now, no matter how you choose the first person's birthday, your second student, all you know is that the second student's birthday is different from the first one. So whatever you chose for the first one is off limits now. And there are 364 choices for the second one. And so on. For the third student, there are now both of these birthdays are off limits, and so there are 363, and so on. 365 minus n plus 1. So which is the same as 365 factorial divided by 365 minus n factorial. Yeah? Doesn't matter. You can just write it out as you want. And the probability of B is just this number divided by 365 to the n. So it's whatever. It's 365 times 365 minus n plus 1 divided by 365 raised to the power n. Now, if you calculate this number out and you work it out for different values of n, what you'll find is that for n equal to 20, this is about 0.41. For n equal to 22, it's about 0.48. For n equal to 25, it's about 0.57. And for n equal to 30, it's about 0.71. So already somewhere between 20 and 30, it exceeds 0.5. And it rapidly, converges to 1, by the time you're 40, as you move up from 30, it sort of moves very quickly towards 1. Okay? Yes?
Did you get the 365
I'm sorry, how did I get the 365 minus n down here? Okay, so what I said was, that probability is 365 times 364 and so on up to 365 minus n plus 1, right? Now, what's missing? If you wanted to make the numerator 365 factorial, what's missing? So what would you multiply the numerator by to make it 365 factorial? Well, you just continue this series, right? The next term would be 365 minus n. The next one would be 365 minus n minus 1, and so on. So this entire expression would be 365 minus n factorial. So I multiplied the numerator by that, and multiplied the denominator by that. So the numerator now becomes 365 factorial, because I completed that product all the way down to 1. And then I get this left over in the denominator. Okay. Okay. Yes.
For omega, we considered all the space in which the order matters.
Yes.
Could we have just taken omega to be the space in which the order doesn't matter? Because it seems like it's asking the question where the order doesn't seem to matter.
Yes, but you could try to do that, but unfortunately the size of the sample space then becomes a little harder to figure out. You know, the cardinality of the sample space becomes a little harder to figure out. Because when you have repeated birthdays, right, when you try to unorder them, it becomes a little harder. So if you can figure out the size of omega where the order doesn't matter, you're welcome to do it, right? It's just a little harder to do. Yes?
Isn't the probability that we calculated for B not for A?
Oh, right, good. Yeah. So, yeah. Okay. This was the probability for B, not for A. So what's the probability of A? Yeah, so the probability of A is 1 minus the probability of B. Okay, because our picture is like this. That's B, and then A is whatever is not in B. And so the sum of the two probabilities is 1. And so these figures that I gave you, these were actually for the probability of A. Yeah, thank you. There's another. Okay. Let's do another thing very quickly. Let's try to figure out why didn't we just directly calculate the probability of B? Why didn't we just work out the probability of B? No, sorry, of A, right? Which one were we interested in? A, yeah. So why didn't we just directly work out the probability of A? A was, well, the probability that any two of them have the same birthday, right? So can't we work that out? Could we work that out? I mean, what's the probability that two of them have the same birthday? So this would be cardinality of A divided by, well, if we keep our sort of people ordered, right? Then it would be divided by 365 to the n. Or if you work it out for unordered, you know, whatever you want to do. But then how do you figure out the cardinality of A? Yes?
Probability that 2 share the same birthday, probability that 3 share the same birthday, 4, etc., up until n.
Yeah. Okay, so you might say, you might try to figure out what's the probability 2 of them share the same birthday, 3 share the same birthday, and so on, all the way up to n. And then what about the rest of them? So let's say 2 share the same birthday. What about the rest of the n minus 2? How do you deal with them?
They all share different birthdays.
Okay, so you would figure out the probability that exactly 2 have the same birthday and everybody else has different birthdays. Exactly 3 have the same birthday and everybody else has a different birthday, and so on. But does this exhaust all the possibilities? Yes?
No, because there might be 2 pairs.
Yeah, there might be 2 pairs or 3 pairs. So it would be a massive headache to try to figure all this out, because you'd run into so many cases, right? So what's the moral of all this? Well, you know, not every set is nice. Not every set, you know, you cannot count every set. Which are the sets that we can count easily? It's the ones where we can apply our rules of counting. Okay? Our rules of counting are very powerful, but they are somewhat limited. You know, they work in certain cases, and they work often enough that we can actually compute lots of probabilities. But sometimes they just don't work. So what do you do? Well, you look at the set that you're really trying to count, and then you try to express it in, maybe your rules of counting don't work for it directly. But then often you can find some other closely related set which you can apply the rules of counting to. And then you do that. And that's how you do counting. Right? So that's why we wanted to count A, but we couldn't. So we looked at omega minus A, which is B. B we can apply these rules of counting to. Yeah. So that's a good thing. Okay, so much for that. Let's do our second example. This is called the Monty-Hall paradox. Okay, so remember what the paradox was? There are three doors. Behind one of these doors, the game show host places a car. Oh, I don't know. Okay. Behind one of these doors, he places a car. Behind the other two, he places, your standard issue book. Okay. And the contestant chooses one of these doors. So the contestant chooses one of these doors, let's say the first one. At this point, Monty-Hall, or his assistant, opens one of the other two doors, right? To reveal not the car, but a goat. So in this case, there's exactly one door that he can open. So he opens this one, and then he gives the contestant the chance to switch between the door he had picked and the other unopened door. The question is, should the contestant switch? Okay. So now there are two ways to reason. So clearly, when the contestant first makes a choice, the probability of success with first choice is exactly 1/3, right? So nothing's happened yet. He's just chosen at random, and there are three doors. The chance of picking the right one is 1/3. The question is, what's the probability of success with the sticking strategy versus what's the probability of success given the switching strategy? Okay. And one kind of reasoning says it should be 50-50. Right? So reasoning one says it should be half-half because after all that the contestant now knows is that there are two doors, the prize is behind one of them, it's 50-50. Okay? The second kind of reasoning says nothing changed about the door that he had selected before. It's still 1/3 chance of success if he sticks with the door that he originally picked. And so it must be the case, since there's only one other door, that the switching strategy has a 2/3 chance of success. Okay? How many of you have seen this paradox before? Almost everybody. How many of you have not? How many of you understand this paradox? Most of you. Okay. So you're doing, let me just say that you're doing better than Monty-Hall himself. Can you read this? Okay, so it's a letter from Monty-Hall to a professor at Harvard, which, here's what it says. This professor had written to him saying, is it okay to use, you know, to refer to this Monty Hall problem or paradox in a book. Okay? Do you have any copyright objections? And so Monty Hall wrote back saying, I'm sending you my okay. And then he says, you mentioned in part A, the player should switch doors even without additional compensation. Indeed, the player should be willing to pay Monty up to, okay, I don't know what the context is, there's some particular price, up to $21,000 for the privilege of switching. Now, I'm not well versed in algorithms, but as I see it, it wouldn't make any difference after the player selected door A and then having been shown door C. Why should he then attempt to switch to door B? The major price could only be in one of the three doors. He has made his selection of one of the doors. He has been shown one of the doors that contains the booby. Ergo, the major prize will be either in the one he selected, door A, or the one that remains, door B. Why would he be compelled to switch doors and even pay for the privilege? The chances of the major prize being behind door A have not changed. He still has one of the two remaining doors. What makes door B such an attraction? I would be pleased if you would write me explaining this situation. Okay? So let's see if we can work through the explanation again. Okay. So there are two ways to think about the problem. One is purely probabilistically, and the other is by working through the sample space. So let's do both of them. The first one, thinking about it purely probabilistically, there are your doors A, B, and C. Let's say the contestant picked door A. Okay. So now there's a 1/3 chance that the car was behind this door. Okay. The car is not moving anywhere. Nothing's going to change about it. Right? Monty can open the doors in any order he wants. As long as the contestant stays put, his chance of success are exactly 1/3. Right? For dramatic effect, maybe Monty first says, let me first open door B, and then door C, and finally door A. Doesn't make any difference, right? Either the contestant won or lost, right? The fact that the doors were open in a different order doesn't make any difference to that, as long as the prize stays put. Yeah? Okay, so that says the chance that the contestant wins with a sticking strategy is exactly 1/3, no matter what order the doors are opened in. But now, Monty happens to open the doors in a certain order where he opens whichever of these two doors has a goat behind it. And if there's a choice, he picks one of them, using whatever means he wants, maybe at random. Okay, so he opens door B and reveals that there's a goat behind it. Okay, now what do we know? We know that, okay, and he does this always. So he always opens one of the doors and reveals that there's a goat behind it. So at this point of the game, we know that the contestant has still won with probability 1/3 exactly, right? Overall, right? No matter what happened, in all the situations together, he won with probability 1/3. In all those situations together, Monty Hall happened to open one of the doors and showed that that's not where the prize is. So now there are two doors left. The prize is definitely behind one of the two. The chance is 1/3 that it's behind the one the contestant picked. So it's exactly 2/3 that it's behind the one that he did not pick. Right? Okay, so that's probabilistic reasoning. Now if you want to make it completely formal, you might want to do what's called, you might want to look at the sample space. Right? And okay, so let's try to understand what the sample space looks like. So the way we understand the sample space is we say, we'll draw what's called a tree diagram. So first of all, there's one of three places where the prize could have been placed. So let's write them like this. So either the prize was here, or it was here, or it was there. Right? So these are the three situations. Right? Either it was behind the first door, second door, third door. Then there are one of three choices that the contestant makes in each of these three cases. Right? Either he picks the first door, or he, oops, sorry, that was not right. Or he picks the second door, or he picks the third door. Right? Same thing in these three cases. I'm not going to draw them, but it's all by symmetry, right? It's completely symmetric. And then, okay, so this is the prize, this is the contestant, and then what happens? Then Monty chooses which door to open. So in this case, he has two choices. He can either choose this door or that door. Okay, so how should we mark that? Let's call that open. And then, right, he has a choice of two doors to open. How about in this case? There's exactly one door he can open, right? Because that's the prize door. That's the one the contestant chose. Of the two that the contestant did not choose, this has a prize behind it, so Monty can't open that one, so he's got to open that one. So there's exactly one that he can open, which is, oops, sorry. So he's got to open that. And similarly, in this case, he's got to open one of them. You know, he's forced to open that one. So now we can figure out what's the probability that the contestant wins under the switching strategy. Well, he wins in the switching strategy in which of these cases? Well, in this case, he had picked the correct door. If he switches, he loses. Right? So in this entire case, he loses. What's the probability of this? It's 1/3 times 1/3. Right? So the probability of each of these, 1, 2, 3, 4, 5, 6, 7, 8, 9, is exactly 1/9. Right? There are 9 cases, they're equally likely, each has probability 1/9. So in this one, he definitely loses. So meaning he loses in both of these possibilities. Right? How about in this one? If he switches, he wins. In this one, he wins. Right? So there are 2 cases in which he wins. And by symmetry, there are 2 more here and 2 more here. So there are exactly 6 out of 9 cases. 6 cases in which he wins. Each of them has a success probability of 1/9. Therefore, the probability of success is 6 times 1/9, which is 2/3. Okay? Is it clear? I mean, this is sort of, it's belaboring a point, but, sometimes things get tricky, and then, if you're not confident about your probabilistic reasoning, you have to work through this diagram, and you've got to work out what does the sample space look like. And if you have a sequence of choices, then you can use a tree diagram to say for everywhere you made the first choice, there are this many ways of making the next choice, and then there are this many ways of taking, etc. Yeah.
Could you go over that final bit of the sample? Like, I got the tree part.
Yeah.
And what is the final sample?
Oh, okay. So what does the sample space finally look like? Well, finally, by symmetry, there are 1, 2, 3, 4 times 3 points in your sample space. What do we know about each of these points? This has probability 1/3. This has probability 1/3. These two together have probability 1/3. Right? What's the probability of each of them? Well, it depends upon how Monty chooses to open the doors in the case where he has a choice. He might always pick the leftmost one, in which case this would have probability 0, this would have probability 1/3. He might pick at random, in which case this would have probability 1/18, this would have probability 1/18. The two together have probability 1/9. So let's say that's what he does. Right? So this has probability 1/18, 1/18, 1/9, 1/9. And then you have the same sort of picture here, same sort of picture here. Right? So now we step back and we say, okay, now which of these sample points does the switching strategy win in? Right? So, well, we look at this one. The contestant picked the correct door, but now he's switching. That's a bad idea, but okay, he loses. He loses in this one, he loses in that one. What about this one? Well, he chose the wrong door. Monty opened that one, so then he switches here. He got the prize. Good, so he wins under switching. Similarly, he wins if he switches here. So what's the chance that he wins if he switches? Well, there's 1, 2, and then by symmetry, 3, 4, 5, 6 cases in which he wins. Each of them have probability 1/9. So he wins with probability 6/9. Okay, so what's the difference between the first picture and this one? Well, it's really talking about the same thing, except, we are just burrowing through to the details in the second case. It's what you know about in many, many different contexts, right? If you're writing a program, you can sort of sketch it out and you can say, this is what I plan to do. You know it's going to work, but then you've got to write it out and make sure it works. You're writing a proof, you can say, well, this is what the proof should look like, but then you write it out and make sure it works. Right? And that's what we're doing here. Yeah? Okay. Yes?
What will happen if we have more than 3 doors, like 5 doors, and each choice, the showman open 1 door for us, and we have the choice of choosing or not? Will the chance at the end get higher? Or?
Well, you're saying, let's say that Monty only opened 1 door, behind which the goat was. And and then you still had a choice of, whether you switched or not. What should you do? And let's say there were 5 doors. Right? So we could reason again like this, right? We could say, look, there are 5 doors. The chance that you picked the correct door to begin with was 1/5. Okay. So now what happens afterwards? What happens if he opens one of the other doors and shows you that the prize is not there? Well, first of all, you know that the prize is behind one of those 4 doors with probability 4/5. Right? So you know the probability of success was 4/5 among those 4 doors. And now he's shown you one of them does not contain the prize. So he's, of these 4 doors, he's eliminated one of them. Okay? Now what happens if you pick one of these at random? What's the chance that you get the prize? So together, the chance is 4/5 that the prize is somewhere behind these. I claim that if you pick one of them at random, the chance would be 1/3 times 4/5 that you'd get the prize. which is 4 over 15. Before, with the sticking strategy, if you stick, then the probability of success was 1 over 5, which is 3 over 15, right? So your probability goes up from 3 over 15 to 4 over 15 if you switch. Okay. Now there's a completely different question you could ask, which is, what happens if instead of opening one door, well, now there are 4 more doors, right? There are 5 altogether. Of these 4, we know at least 3 don't have the prize behind them. And what if Monty actually opened 3 of those doors? Now what would your chance be of succeeding if you switch? Right, so you had 1/5 chance before. Now if you switch, you should have a chance of 4/5. You see, because, as the number of doors tends to infinity, imagine that there are n doors. N is very, 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 very large. So you know that the first time you if you pick at random, the chance that you got the correct door is negligible. It's 1 over n. It goes to 0 as the number of doors tends to infinity. But now, if Monty is going to run around and he's going to open all the doors except the one you picked and one more, and he's going to show you none of these other doors have the prize behind them. So now you're left with just these 2 doors. Obviously you should switch, right? Because your first choice, it was so unlikely. And he's done all this work showing you that all these other doors don't have the prize behind them. You may as well switch.
So the chance of winning by switching gets closer to 100%?
It will get closer and closer to 100% because your chance of winning with the original, if you stick to the original door is 1 over n. So the chance that you win if you switch would be 1 minus 1 over n. Okay. Let's see. Should we do one more thing or should we take a break? Break? Let's take a break. I'm sorry? Yeah. That's fine. That's fine. Okay. Incidentally, how many of you actually watched the debate last night? Oh wow. Okay. And how many of you are following the polls, the presidential polls? I'm sorry? Oh, I see. How many of you know about this website called 538.org? I'm sorry? It's okay, so, well, you should look it up. It's quite interesting. You know, so polling is something we'll talk about later in this semester. You know, how can you know what what opinion, 200 million people have, right? By just asking a few of them. How can you get a reliable estimate? And then it turns out that there's even beyond so we'll talk about it in sort of very abstract terms. But then to translate that into practice takes quite a bit of doing. And there's this particular, well, it was a blog which has now been taken over by the New York Times. So it's a blog that's featured on the New York Times called 538.org, I think it's all, by Nate Silver, who, did he work with the Oakland A's? I'm sorry? I think the story is he worked with the Oakland A's, right? He helped them put together, a winning team, even though they were one of the poorest teams in the league. And he did this by applying statistics well. He picked he sort of applied all these tools about how to understand the data. And then a few years ago, I think around 2007, 2008, just before the last elections, he went into doing the same thing for politics. Because the media were doing such a shoddy job of reporting polls, that he sort of decided that it was about time that an adult stepped into the business and showed them how it was actually done. And it was quite remarkable. I mean, he sort of got the entire thing right. And, as opposed to the media which were running around saying, there's a poll which shows this, and there's one which shows that, and nobody can tell, and so on. And actually, the information was all there. You just needed to analyze it. And so he still runs this website with those numbers and so on. And it's actually quite interesting. You should look it up. Okay, so we'll talk about polling in a few lectures. We are not quite there yet. So what we're going to talk about now is we'll talk about conditional probability. Okay, conditional probability is, let me just say at the outset, it is not a difficult subject. It's actually very simple if you understand the basics. So let's try to understand the basics. Okay, so let's say that you have a bag in which we've placed a number of chits of paper. Okay, each of them with a 0 or 1 written on them. Okay, so let's say that the chits come in two different varieties. They are the black ones, on which we have written either 0 or 1. And then there are the blue ones, okay, on which we've written either 0 or 1. So there's some number of black chits and some number of blue chits. Okay, what you're going to do, you're going to reach into this bag, pick out a chit at random, and look at what what the chit says. Is it 0 or 1? So what's the probability that you see a 1? Well, it's exactly the number of ones divided by the total number of chits. So it's 1, 2, 3, 4, 5, 6. 6 over 10. Okay. But now, it turns out that you can't help yourself. You pick out this chit, and you look at the color of it. And you notice, first, that it happens to be blue. Okay. Now what's the probability that it'll show you a 1? It'll be 1/4, because as soon as you see that the chit is blue, you're in this side of this sample space. You're no longer, you knew you were picking one of these chits at random, but you know it's the one on the right. Yeah? So it's one of those 4, exactly one of those has a 1, and so the probability that you see a 1 is exactly 1/4. So the way we write it is the probability of 1 given blue is 1/4. Yes? The probability of 1 given black. So you pull out the chit, you look at it, it's black, and now what's the probability that it's 1? 5, 6. Okay, so this is conditional probability. Okay? But now, we can sort of turn it around, and we can say, suppose you pulled out this chit, and you looked at the number first, and you saw it was 1. What's the chance that it's blue? Is 1/6. Okay. So now let's try to understand these things how we got these answers. Then we'll introduce the notation. It's going to be, if you just keep the picture in your mind, it's just very elementary. And then we'll talk about Bayes' rule, which is the main rule by which we do inference. Okay? By which we do probabilistic inference. This is the main thing, this is sort of the most fundamental thing in probabilistic inference and in AI. It's just a very simple rule once you do it in pictures. And then, but we'll do it in pictures, we'll write down the notation, and then you won't be afraid of the notation anymore. I hope. Okay, so what are we doing? So first of all, let's figure out what's the probability of 1 given blue. Is what? Well, it's the cardinality of this set, right? So it's the probability that you see a 1 intersect blue. So let me define some things. So let me define the set 1. This is the set which I'm calling 1. Right? I'll call this set 1. Is that okay? Are you happy with it? If you want, I'll call it S sub 1. And then this other set, which consists of these zeros, I'll call S sub 0. Okay. So now, what's the probability of 1 given blue? It's the probability of you are in the set S sub 1 and in blue. It's the intersection of these two, which is what? Which is this SOL 1. It's the cardinality of this set divided by the cardinality of blue. Right? So there were exactly 4 elements in the blue set. There was exactly 1 element in the blue set which was labeled 1. And so the probability is 1 over 4. Okay? So in general, we'll say suppose you have an event which we call A. Right? A is like this event that the outcome equal to 1. And you have another event B. B is the event that what you saw was blue. Right? And what we are saying is that the probability of A given B is what? So now that you know B occurred, you are in this situation. And so what you want to know is, if you want to know that A, what's the probability A occurred, you look at, this is the chance that A occurred given B occurred. So it's just the probability of A intersect B divided by the probability of B. Yes? Does this make sense? So we are saying this is our sample space omega. This, with probability 1, something in omega happens. But now we are told that actually we picked a sample point, it happened to be in B. And now we want to know what's the chance A actually occurred. Okay, so what do we know at this point? We know we are somewhere randomly in that set B. Okay? For A to occur, we must be in the intersection of A and B. So what's the chance that that happens? Well, we already know that B occurred, right? So we must divide by probability of B, because that used to be small. Maybe it was 0.25, but now we know it has already occurred. So we want to make that equal to 1. So we want to scale by that. But we want to know what's the probability that both A and B now occur. Okay, so so now suppose that let's go back to this example, and okay, so let me actually draw this example all over again, and we'll work through it, and we can sort of try to. Okay, so this was our example. We had we had 2 sets which were black and blue. Let's say we had and we had our blue set which looks like this. Okay, so this side is this side is black, this side is blue, this side is 0, that side is 1. Okay, and so we have different numbers we can figure out. One is, what's the probability of 0 given blue? Is a half. Probability of 1 given blue is a half. Probability of 0 given black is 2 over 6. Probability of 1 given black is 4 over 6. Okay. Now, suppose that this is an inference problem we have. So black and blue are sort of two different medical conditions people could have. Okay? And let's say 0 and 1 are outcomes of a certain medical test. Okay? Let's say black or blue is one of the medical conditions you could have. Okay, and 0 and 1 are the outcomes of a certain medical test. And let's say that you already know that 40% of the population is blue, 60% of the population is black. Okay. You also know that you also know these probabilities. You also know what's the chance that your test comes out 0 or 1 in each of these two cases. So this is something that has been done through medical research. Okay. And now somebody goes in and gets the test done. Okay. So some particular person, who we are thinking of as a random person, goes in and gets the test done. So somebody goes in and gets the test done, and it turns out to be so we have a random individual, and the outcome of the test is a 1. Okay? What we want to know is, given that the outcome is 1, what's the probability that this individual lies on this right side of the divide, on the blue side of this picture? So what's the probability of blue given that the outcome of the test is 1? Okay? Right. I claim that, okay, so this is what conditional probability allows you to do. This is exactly what's called Bayes' rule, Bayesian inference, or Bayesian inference. And how would you do it? Well, you'd basically, if you were going to draw a picture, this is what you'd draw. You'd say, well, the probability of 0 given blue is a half, probability of 1 given blue is a half, etc. Right? The 40% of the population is blue, 60% is black. So that's what the picture looks like. And now what you want to figure out is, given that the outcome of the test is 1, what's the chance this individual is blue? Well, you can read it off that picture, right? You can say, well, the number of individuals who, for whom the test gives 1 is exactly 6. 2 of them turn out are blue individuals, 4 of them are black, so the probability of blue is exactly 2 over 6. Okay, so the answer is exactly 2 divided by 6. So you could solve this. You could solve this by picture like this. What Bayes' rule gives you is a formula by which you can actually work all this out. Okay, instead of having to draw this picture and try to figure out what those proportions are, what it does is it gives you a formula. And so, so the way Bayes' rule works is, you're given a population, and you're told there are two kinds of, there are two types of individuals. There are the individuals in the set A, and then there's A complements. Right? So there are two types of individuals, A and A complement. There are two types of test results, B versus let me put that in black. So B versus B complement. Two types of test results, B and B complement. Okay, so this could be 0, that could be 1. What you're told is, you're told probability of A bar. So you're told what fraction of individuals are in the A side of the bracket, what fraction are in the B side. You're also told probability that an individual picked randomly from the A side, the test comes up positive, right? Actually, sorry, let me, two types of test results, let's call them positive and negative. Okay, it's a little more evocative. So let's say that these test results we are calling positive, those we are calling negative. So what we are told is, what's the probability of positive given A? And what's the probability of negative given A? Sorry, we know this, right? So we know that is equal to 1 minus probability of negative given A. But we also told the probability of positive given B, given A bar, which is 1 minus the probability of negative given A bar. Okay, so we are being told the proportion of the population which is of type A versus type A bar. We also told, so these are, A is the population which is suffering from the condition. A bar is the population which is, so let's say you're doing a test for cancer. A is the population which suffers from cancer. A bar is the population which does not, right? You do a certain test. There's a probability that a random individual who has cancer is going, the test is going to come up positive for them. There's a probability that it'll come up negative for them even though they are suffering from cancer. For somebody who's not suffering from cancer, there's some chance that the test will again show up positive, and there's some chance that it'll show up negative. What you want to know is, suppose you sample suppose that you have sampled a random person from the population, and suppose that the test came up positive. What's the chance that they actually suffer from cancer? Right? This is the inference problem. So what we want to know is, what's the probability of A given that the result was positive? And the answer is, well, by the definition of conditional probability, it's the probability of A intersect B divided by probability of A. Oh, sorry. My choice of P here was quite unfortunate in terms of notation, because I'm going to have to write down here P of P, which I don't want to write. So let's call this something else. Positive, negative. What else can we say about test results? They come up. I'm sorry.
Or you can just use a plus sign for P and an N if it's negative.
Very good. So let's call them plus and minus. Okay, so let's call this plus, minus, right? Further, the probability of plus we can write as probability of plus intersect A plus probability of plus intersect A bar. Okay. So now, when you put all this together, what you would get is the probability of A given plus is the probability of plus given A times the probability of A. Because remember what conditional probability tells us. It tells us the probability of A given plus is sorry, the probability of plus given A is just probability of plus intersect A divided by probability of A. And so if you cross multiply, you get probability of plus intersect A is just this conditional probability times probability of A. And what you'd get in the denominator is a similar expression, which would be probability of plus given A times probability of A. That's this part, plus probability of plus given A bar times the probability of A bar. Okay? Now, the point is, these are all numbers that we know. Yeah. Oh. Work? Oh God. Okay, good. All right, so okay, so so let's just stare at this for a little while. So what do we know? Well, what we know is what's the proportion of A and A bar in the general population? What proportion of the general population suffer from cancer, right? So that's something we know. What we also know through medical research is how good is this test, right? So if you have a random person who has cancer, what's the chance that this test will come up positive? We also know if you have a random person who does not suffer from cancer, what's the chance that this test comes up positive, right? So these are the false positives. Okay, so we know all of these probabilities to begin with. And then we have a random individual who comes up who's tested, and we want to know what's the chance that they actually lie on the left side of the picture. What is the chance that they're on the set A? What's the chance that they actually are positive for cancer? And so what Bayes' rule does is it allows you to take this conditional probability and flip it around. Okay? So you know that this person has tested positive. Now you want to know what's the probability that they actually suffer from this condition. And so you say, this is exactly the chance that if they suffered from the condition that they test positive times the chance that a random person suffers from this condition divided by the same thing, the same expression, plus the chance that they test positive if they did not suffer from the condition, times the probability that a random person would not suffer from this condition. Okay? Okay, so here's another way to see it. The other way to see it is, look, to begin with, before we did the test, what did we know about this person? What was the chance that they had cancer? Well, let's say that even though I'm drawing it like this, let's say that A was, the probability. Let's say that the probability of A was, I don't know. Let's say it was 0.5. Okay, this is a pretty bad. We hope it's not this, but let's say that this was a chance of suffering from this condition for a random person. Okay, not so good, but now we do the test. We perform the test. And it turns out to be positive. Now what's the chance that this person suffers from the condition? Well, now we know that conditional on the test coming up positive, this is our universe. It's no longer what it used to be. This is where we are sitting. So what's the chance that the person now suffers from cancer? Well, it's the area of this region divided by this whole thing, right? So chances have gone up tremendously given that it came up positive, even though there could have been a positive outcome on either side of the line, right? And so Bayes' rule allows you to do this. It computes this area divided by this whole area. Right? That's what we did here. It's the probability of A intersect plus divided by the probability of plus. That was this particular area divided by this whole area. Okay. Then what did we do? Then we turned it around and we said, what's this area? Well, we said, let's look at it as part of this. It's the probability of plus given A divided by probability of A. So as a proportion of this area, which is probability of A, it's what fraction of it? It's that fraction, probability of plus divided by probability of A, or probability of plus given probability of A. It's that proportion of the area of A. Right? What about this whole area? This whole area consists of two parts. There's this part, which we copy down here, and then there's this piece. So what's that area? Well, then we said, what's this area as a proportion of A bar? Well, it's probability of A bar, that's the entire area of A bar, times what proportion of it? Well, it's probability of plus given A bar. So that's this expression here. Right? So what we're doing is exactly these area calculations, right? That I showed you on the right in the beginning, except we are doing it symbolically. Okay? So it's one of these things which now you should just try working through, and it's it's something that you just have to work your way through and see that you understand that the visual areas correspond to those expressions. Oh, by the way, sorry. One quick thing before you leave. The midterm is in class next Tuesday. Sorry. Yeah, does it come as a surprise, or everyone knows? Okay. The midterm will cover everything through, conditional probabilities and Bayes' rule. So it'll cover everything through this homework that's due this Friday.